So this is Manoj Vaddineni, and I'm the Business Development Director for APAC for VIAVI. So today we'll talk about Gen5, and then a brief introduction of all the speeds within Gen5 within PCIe, and then also the adopters of PCIe and then an update on Gen5, PCIe Gen5 technology, and then we'll also talk about test scenarios and solutions. So, as you all know, PCIe has been around for about 17 years now, and PCIe Gen1 started out in 2003. And now the latest speed that the industry is looking at implementing is PCIe Gen5, and PCIe Gen5 operates at 32 gigabit transfers per second per lane. So and the spec has been ratified for a while now, and you're seeing early systems that come out from the industry. But the spec has been around since May of last year. So there's no certified products out there yet in the market, but I think the industry is seeing early engineering samples from different vendors. I have a slide here which talks about all the speeds and the bandwidths at each generation of PCIe, and as you can see, Gen5 now is now at 32 gig transfers per second, which basically gets you about 512 gigabits per second. So the base specification, as we talk about, it's been done in May of last year. The chem has been the development is also done, and the compliance testing. I think we hope the industry, the PCI SIG, will put something out by mid of next year or later part of next year, and basically Q3 or Q4 of next calendar year, you should see some level of certified products out there in the industry. So I have the ecosystem, just an the customers that I've talked about, or the different vendors that I've talked about in this slide. I'm not claiming they're Gen5. All I'm talking about is who are the different vendors for each of these segments. So we'll not be talking about their Gen5 plans, and anything that is public information, you should be able to go check it out for these individual companies on their Gen5. So from an IP perspective, you have ARM, you have Cadence, PLD, and Synopsys. There are going to be multiple SoCs based on ARM, and PCIe is going to be one of the primary interfaces on it. From a CPU perspective, you have AMD, HiSilicon, Intel, NVIDIA, Qualcomm, and and the others. So same thing with switch and retimers. At Gen 4 you had Broadcom and Microchip, which was and then from a retimer perspective, Astra Labs and Texas Instruments. For graphics controllers, you would have AMD and NVIDIA, and the different I/O controllers, you've had Broadcom and Microchip. So I think the storage ecosystem is much bigger. The traditional SSD drive vendors, whether it be, Marvell controllers or Micron, Samsung, SK Hynix, Toshiba, WD, and, you know, and all the others. From systems perspective, you have Cisco's, Dell's, and HP's, and IBM's that have been, traditional system vendors. And there is a huge ecosystem of data center adoption by companies like Alibaba, Amazon, Baidu, Facebook, Google, Microsoft. And there would be a huge ecosystem of ODMs that do design and and validation and supply of different systems for the people, for the companies in the data center ecospace. Okay, so where does the protocol analysis go into? Basically, it goes into all the IP market, IP customers, then CPU, Ethernet controllers or NIC cards, accelerators used in deep learning and machine learning, and artificial intelligence. The systems market, basically data center servers, high performance computing, and you have other mission critical and low latency critical applications like autonomous driving, defense, and finance/security applications. So, what are the different groups that basically use protocol analysis? Is you have your validation, system integration, IP emulation, and IC components validation, systems and networking equipment, and as well as your support teams, your design win teams that for components, drivers, and interoperability debugging, as well as performance tuning, and also some advanced function analysis like power management and link and failover, safety failover situations. So, as you know, Gen5 is 32 gig giga transfers per second, and it is backward compatible. It leverages most of the features from your Gen4, with most of the changes being in the Phi layer. Phi layer being the logical Phi from a protocol perspective, and the electrical. Most of the data link and transaction layers have remained the same. So generally in the industry, when you move from one speed to another speed, most of the bugs that you would see, 55% of the bugs that you would see when you go from a certain speed to a new speed, they are all in the physical layer or the Phi layer, which is the logical sub-block is where the protocol kicks in. And most of the issues are related to this, which is basically the PCS layer. Similarities with Gen4, it's backward compatible, same signaling, scrambling, and bit encoding schemes. The burr is the same as in Gen4. TX presets, they are the same from P0 to P10. And basically, most of the testing approaches that you've used at Gen4, you can use the same at Gen5. No major changes to the transaction layer, and the same scaled flow control and extended tag benefit. Extended tag bits, you can benefit that at Gen5 speeds. The Gen5 electrical updates, electrically you've moved from Gen4, which was 16 giga transfers per second, to 32 giga transfers per second. Jitter is 2 times and around 3 times the clock reference clock jitter reduction. And I've basically referenced the sections in the spec that you can refer to. Channel loss budgets around 28% greater than Gen 4. So recommend that you use a very high quality PC, very low loss PCB materials and short channels if possible. And I think retimers, as based on your experience at Gen 4, retimers would probably be, very, very much required for longer channels. So lane margining on RX, this is something that was introduced in Gen 5, and I think that would be one critical feature on your electrical that most you would have to take advantage of that. Okay, basic changes in the Phy layer. EIOS is now instead of 16 zeros, it is 32 zeros and ones to detect exit from electrical idle. Back-to-back EOS are to be sent from exit to EI, from EI to be detected. Symbol bits. It is changed from 55 to 87 hex to detect a Gen 5 data stream. So, and the same thing, symbols 0 to 7 for ordered skip ordered sets is changed from 11 AAH to 99 hex. And new bits are added in TS1, TS2. So this is to support 32 gig transfers and equalization options and precoding options and alternate protocol negotiation. So new bits, as you can see, the new bit is the, to identify the 32 gig, whether 32 gig Gen 5 is supported, and if so, that to denote that bit is on. So, and also precoding. So you want to see whether the precoding bit is on or off. So another thing is that whether you go through the full equalization or you can skip the full equalization and go from Gen 1 to Gen 5. So because if you go through the full equalization, EQ can take hundreds of milliseconds per speed change, right? So what Gen 5 gives you is the ability to, if you want to bypass it, you can bypass from Gen 1 and go all the way and go right away to Gen 5. And that's when you have no EQ. And basically it skips through all the equalization at all the rest other speeds. So EQ bypass options are negotiated as using the TS1 and TS2, and those particular bits are here as you can see in this slide. So alternate protocol over Phy, PCIe Phy. So as you know, there is going to be CXL, and CXL is a which stands for Compute Express Link, and it's becoming very prominent now. And with especially AI, deep learning, and machine learning, CXL is and the consortium has quite a few number of vendors that are part of that consortium, and the spec, which is at 1.0 now, is moving very quickly, and I think there are chipsets that are going to be out there soon with the CXL support. So what CXL is, so right now in the TS1, TS2s, you have the protocol ID, and you can see these additional bits where they will tell you whether it's CXL, and if CXL, what is the alternate protocol that uh, you can negotiate. Okay, and what are the different capabilities that are supported with CXL has a variety of whether it's CXL cache, MEM, or IO. So these bits will tell you whether that device supports cache, MEM, and IO, CXL.io. You can see both in TS1 and as well as in TS2s. Quick one, CXL is an open industry standard interconnect. All it does is it uses the exact same physical interconnection from PCIe, except that the Phy is when, as part of your TS1, TS2, if you have an alternate protocol and that can be CXL. So basically your PCS changes from a regular PCIe, the link layer, and PCS changes to a CXL. So CXL has three different protocols: CXL.io, CXL.cache, and CXL.mem. So it's again, it's all the accelerator modules that you see to enable really low latency IO, where you're basically bringing the cache. The devices are able to access the host cache, and the host is able to be able to access the device's memory directly, and that is what is basically cutting down the latency for accessing cache and mem. And for this really accelerates some of those applications that really need low latency cache and mem IOs. So CXL.io, again, CXL has three different types of modules, basically type 1 device, type 2 device, and type 3 device. So based on the type, certain devices, basically based on whether they need a cache or whether they need cache and mem, or whether they need just memory, they are categorized to a certain type. So type 1 is mostly accelerators, smart NIC cards, basically devices that coherently access the host memory, and that's basically the coherent cache. And type 2 device, accelerators with attached memory and coherent cache. So devices are able to access the host memory, coherently access the host memory, and host can access the device's memory. So that basically allows for a very fast cache and memory access across the host and the device. And the type 3 devices basically are memory buffers and expanders. So all it does is host accesses and manages the host's devices. The devices manages the device's memory. So, now we'll get into the different test scenarios. So, how would you identify, the EI exit? So basically, if you take VIAVI as an example, you can see the EIAOS and followed by the electrical idle, and how, as to when you're, when the link goes into EI. And so also there are ways to go monitor the link recoveries and the signal health in L0 state. So one of the key things that you want to know when you're in the L0 state and you want to know the link stability, so you can be looking at the number of recoveries and replays, and that basically tells you the uh, the link stability, as well as the post capture analysis will tell you the NACS replace and sequence number tracking, which is that's where the analyzer really comes into play. So when you're monitoring a link, one of the key things that you want to look at is the number of TS1, TS2 transitions that you're having, and how many number of TS1, TS2 transitions are you seeing per second, and as well as if you want to go look at all the other PCIe errors at the file layer, you'd be able to monitor those, and that should tell you, just by looking at this dashboard, you would be able to understand what kind of link, how stable is this link, and what's the health of that link. So data link layer, flow control tracking is one of the key things. So what the analyzer should be able to do is to look at your flow control, the number of the credit buffer that is available, credits that are available, and whether there is going to be a credit starvation. So, and what the analyzer does is, in post capture analysis, it goes and measures that credit limit, and it gives you an alert in the post capture analysis as to how many times have you been hitting that credit limit. So a continuous starvation of the credit buffers tells you one of the sides is not behaving, is not able to keep up with the other side. You can also look at transactions, pending transactions, and IO completion times. So this basically tells you how fast your IOs are getting completed. Are any of the IOs are any of the IOs getting stuck in for lack of resources or data in the buffer, or because of credit starvation? So the pending IOs and having IOs out of sequence, and all of these, an analyzer should be able to tell you, and it should be able to tell you, the status of these pending IOs, so you understand what exactly is the issue for a IO to be a transaction / IO to be pending for a certain duration. So I think as you work with PCIe and you work with NVMe, which talks about queues, so you should be able to look at number of pending commands for a certain queue, and I think the analyzer basically has the exchange views or transactional views that basically gives you an understanding of the pending transactions and how well the device, how well the IO transactions are completing, and what is getting stuck. So I think, I would have about 30 minutes of time, and I'll give you a quick overview of our VIAVI's portfolio. So out of the 45 minutes that I have, I will leave about 15 minutes for Q&A. So VIAVI has, analyzers for PCIe, fiber channel, Ethernet, and SAS SATA, and NVMe over fiber channel, NVMe over Ethernet. So, and we do have IO generation test tools that you can be using. So at Gen 4, we have had everything that was needed for you to go debug or analyze a PCIe Gen 4 environment. And we are at all the PCIe SIG events, so you would be able to find us. And if you have any questions on understanding, on debugging a certain PCIe environment, or understanding to understand the tools, you're more than welcome to come visit our booth at all the industry events. And that's it from me. Thank you all for coming over. So I'll open this up for Q&A. Thanks.